In this video, we'll look at loss functions that we can use for training autoencoders. So we mentioned in the previous video that an autoencoder is really just a feed-forward neural network where at the output, instead of predicting, say, a class label, we'll be predicting or reconstructing the original input x. So we'll call the input x hat, and so now what we need to train an autoencoder is to define a loss function that will compare x with x hat somehow to measure how good the reconstruction is. And then using that loss function, we can train the autoencoder to minimize it on average on a training set by doing some gradient descent on that loss function. So let's look at some loss functions for different types of data. So imagine we have binary inputs. That is, the input vector x is are vectors that contain elements that are either 0 or 1. The most popular loss function is this loss function here. It's often referred to as the cross entropy. I'll mention in a minute why we call it the cross entropy. We'll just look at the equation. So it's going to be minus the sum over all the elements in the input vector of xk, so that's the kth element of the input vector, times log of the reconstruction of the kth input element, plus 1 minus xk of log of 1 minus x hat k. So let's look at this a little bit more closely. For instance, imagine that for some given k, xk was equal to 1. Then this would be 1 minus 1, so this whole term here would be 0, so we can just ignore it. And so this would be 1. So really in this case, what I'd be minimizing is the loss here, which would be minus. So we have a minus here, so I could remove the minus and just put it right in front here. So we'd be minimizing minus the log of the output. And so if I minimize this, it's the same as maximizing log of the output. So I'm trying to push the output as close as possible to 1. So remember that for binary inputs, we'll use a sigmoidal activation function at the output. So the biggest x hat k can be is 1. So if xk is 1, we'll try to push the output towards 1. Now if xk was 0, then this term would be 0. This would be 0, so this whole term would be 1, so we just have this. And using the same reasoning, then we'd find that in that case, we'll try to push x hat k towards 0. That is, we'll try to push it closer to the actual value of xk. So you can see that this particular reconstruction function is actually well behaved. It's actually minimized if xk is equal to x hat k for all k's. It would actually be, in this case, if xk is either 0 or 1, it would be 0 if we had this, if we had the perfect reconstruction. We call it the cross entropy because, if you don't know what cross entropy is, if I have a probability distribution P of x and another one Q of x, then the cross entropy between the two distribution would be minus the sum over all possible values of that x random variable of the probability of that a particular value of x times the log of the log probability q of x for the other distribution. Now, if x was binary here, so if x was taking only 0 or 1 values, then this sum would be a sum over the probability of x being 0 and then the probability of x being 1. And so this is how you would get these two terms here. So in this case, p of x would be, so p of x equal to 1 would be equivalent to our xk, and then q of x being equal to 1 would be equivalent to x hat k. So we see that we get the case where p of x equal 1, that would be xk here, and this would be x hat here, and then p of x equals 0, well, because it's a binary variable, it's Bernoulli, then it would be 1 minus the probability of being equal to 1, so that's 1 minus xk, log of 1 minus probability of being equal to 1 according to q, and q is x hat k, That's the probability under that distribution of xk of x being equal to 1. So we have here 1 minus x hat k. So essentially we get this form here if we consider the cross entropy between Bernoulli random variables. And then we have a sum of Bernoulli cross entropies because we're summing over all the input elements, so all the dimensions in my input vector. Okay, so that's why we call it the cross entropy loss. If we had inputs that were not exactly 0 or 1, but between 0 and 1, we could still use this loss function here. It would still be well defined in the sense that the minimum will still be when we reach xk equals to x hat k. So that will still minimize this, even if xk can be between 0 and 1. However, it will not be 0. So if xk say is equal to 0.4 and then x hat k is equal to 0.4, then the cross entropy for that input dimension is not 0. So you shouldn't be surprised if your inputs are not exactly 0 or 1 that you don't reach a perfect cross entropy loss. But another alternative, if you have real valued inputs, is to just use the squared difference. So essentially half times the sum over all the input dimensions of my reconstruction minus the actual input squared. So this is the sum of squared differences. We can actually think of it also as the squared Euclidean distance between the vector x hat and the input vector x. And actually often when we're optimizing this, and if the inputs are really real valued in the sense that it can take value between minus infinity and plus infinity, then in this case often we'll use a linear activation function at the output. So x hat would actually be equal to a hat of x. So if you go back in our previous notation, a hat was the pre-activation at the output layer. So we just, if we have real valued inputs, we would normally use a linear activation function. So in other words, no activation functions at the output layer. So that's another alternative if we have real valued inputs. It turns out then that if we use either of these two loss functions, so the cross entropy with a sigmoid activation function or the squared difference using a linear activation function, then in both cases the gradient with respect to the pre-activation at the output layer of the loss is just going to be the difference between the reconstruction and the input. So here I added the t because you imagine you'd be computing this gradient for different inputs. So I'm indexing now the input here, and I'm also putting the index for the reconstruction to say that this is the reconstruction of that input. So you can do the math to verify this, but it so turns out that it has a very simple form. And then to get the gradient with respect to the parameters and perform gradient descent, we can just use regular backpropagation like we've seen it before, because an autoencoder is really just a feed-forward neural network, and just backpropagate the gradients towards all the parameters. One thing that's important to notice, however, is that if we use tied weights, that is, if you use for the reconstruction weights W star the transpose of the encoder weights, the weights into the hidden layer, then in this case we have to realize that the gradient with respect to the matrix W is really the sum of two gradients. It's going to be the sum of the transpose. It's going to be the sum of the gradient of W star transposed, and it's going plus the gradient with respect to W or with respect to the gradient in the encoder part of the network. Okay, and that's because these parameters W are present in the encoder and the decoder, so they get gradients both from just the decoder part and the encoder part. Okay, so that's something important to realize if you implement an autoencoder with tied weights. And now just a quick word about how can we just adapt an autoencoder for different types of inputs. If we have inputs that are not real valued, they might be integer valued, they might correspond to multinomial observations or other types of observations, perhaps more structured. Well, here's a recipe for doing that. So what you could do is first you define a joint distribution over the input space. Choose a distribution over the input space that will depend on some parameters of that distribution, which I'm calling mu here. So it's going to be the vector of parameters of that distribution. And then you choose some parametric relationship between mu and the encoder, the hidden layer of the computed by the encoder. So in our case, we usually have something like a linear transformation and possibly a nonlinearity. And then the loss function we'll use will just be minus the log of the probability of x given mu, but where mu here depends on h of x. Okay? And so we'll just use that as the form for the loss function. In fact, we can recover the sum of squared distance if we use for p of x given mu a Gaussian distribution where the mean is mu and the covariance matrix is just the identity matrix. So if we have p of x, that corresponds to that. And then if we choose that mu is going to be just a linear transformation of the input, of the latent representation h of x, then we recover what I described before as the loss function we'd be using for an autoencoder with real valued inputs. So I'll let you do that exercise, but essentially you see that minus log here is going to cancel out with the exponential and the minus here, so we'd be left with half and this part, and this is just a constant, so we don't have to consider it. So then we'd fall back on the square difference loss function. All right, so that's all for the loss function we can use, and now we have different alternatives and even a recipe to generalize to many types of data.